Welcome. Last time the word torsion has appeared and it reminded me of some experiments I did in 2015 about analytic torsion for graphs. It's a very exciting topic and it's elementary in the sense that you only need linear algebra, unlike the classical topic, which is quite heavy, that there's a lot of technical overhead when you are looking at this Reidemeister or analytic torsion in the continuum. Let me just get started. I also do that to remind myself a little bit. Maybe I will work on this later. I have most of the questions which I'm going to look at are unexplored, in the sense that I don't know how to prove them, and so that also discouraged me a little bit in 2015 to continue. I think one should also honor in mathematics the discovery of some relations. All other sciences this is done, chemistry or biology. If you explore someone finds a molecule, that's exciting. In mathematics this is just not yet appreciated because the proofs are important. You need to provide proofs of what you are doing. But this is kind of experimental mathematics. So lots of experiments, hundreds of hours of experiments. I have to do more experiments to really see what happens. For example, with analytic torsion. So everything is for very general graphs, finite simple graphs. Like this is a finite simple graph here. And we always look, of course, at the Whitney complex, at the structure given by the complete subgraph. So in this case, what we have is we have two-dimensional parts. We have one-dimensional parts mostly. There's also a three-dimensional part here. So there's one three-dimensional simplex here. So we take all these complete subgraphs and this produces a finite abstract simplicial complex. Let's assume we have n sets, then we have an exterior derivative with explicit matrix, n times n matrix, like Poincaré has already introduced. This is very classical. And then we have the Dirac operator d plus d star, which is self-adjoint symmetric matrix with entries zeros or 1 or -1. And then we can also look at the Hodge Laplacian, which then decays as it's just a square of the Dirac operator, which decays into these blocks. These are the form Laplacians. And the zeroth one has already been introduced very early by Kirchhoff. That's the zero-dimensional Laplacian, which you also have in calculus, Steve Grad. And then you have the form Laplacian L1, which appears in electromagnetism, and so on. So we have all this, but we have in this case there would be 4 blocks here, in this case for this graph. There are a couple of lines, 5 lines, maybe 6 lines to get this, to get the kernel of these LKs, which are by homology groups, and then we have also the Betti numbers at the dimension. This is the nullity of this LK. For me, always Hodge theory in the finite discrete was kind of just something kind of obvious, but it's Ekman, Benno Ekman, who has probably done that first, kind of realized that everything can be done without that overhead of elliptic regularity and all kind of manifold structures. So you have here actually a structure which is very much geometric, very much topological. If you take a geometric realization, you often deal with manifolds and higher dimensional structures. And so we have these groups, and then we can also look at the supertrace is very important because the Euler characteristic can be just written down as a supertrace of the identity. So the supertrace is you take the trace of this minus the trace of that plus the trace of this minus and so on. That supersymmetry is very important, but we have these Betti numbers, and the alternating sum of the Betti numbers, actually that's Euler Poincaré, so this is the same thing than the sum k equal to 0 to the minus 1 to the k bk. So that's also the sum, the supersum of the fk, where fk are the f vector given by the number of vertices, number of edges, number of triangles, number of tetrahedra, etc. So this is the Euler characteristic, a very important notion. So one of the kind of nice things is that you have this McKean-Singer, for example, in the Zeichenfroese-Kirschen-Simon book, this beautiful identity, the supertrace of the heat e to the TL is Euler characteristic. And it just follows from the fact that the eigenvalues of the even forms and the positive eigenvalues of the even form and the positive eigenvalues of the odd form come in pairs. There's a very nice symmetry which you can use in a lot of ways. And there's a kind of a story which Atiyah once told in an interview that, you know, his advisor Hodge and Dirac said, but they never talked, and he's very happy about it because what he could do is kind of use this Dirac story and this Hodge story and make it to a big theme in analysis, topology, geometry. Here it's just linear algebra. We have matrices, we can compute the kernels, we can compute the eigenvalues, and we have spectral data which are interesting to study. So when you have a matrix and you take the product of the non-zero eigenvalues, that's called the pseudo-determinant, and then you can also look at the superdeterminant, determinant of this divided by the determinant of that, multiplied by the determinant of that, divided by the, so you alternatingly divide and multiply like with the super trace, and then what you get is actually a consequence of this McKean-Singer is that this super determinant is 1 for every power of L. And it's also geometrically interesting because for the zeroth Laplacian, for the usual, you know, diff graph Laplacian which you have in calculus, this pseudo-determinant is the number of rooted trees. So it's a very classical thing by Cauchy-Binet, and there is also a kind of a broader result, which is if you take 1 plus L0, then you get the number of rooted forests. All these results follow immediately without any kind of further ado from these Cauchy-Binet formulas, which I once proved. And I'm proud about these formulas because most of the work here was actually just verifying that this has not been done before. So this is a general n times n matrix F and G, and what we have is we can express this pseudo-determinant as a sum of products of minors. So these are all minors of size k, where k depends on this is the maximal rank which you have. And when you take 1 plus ftg and you sum over all possible minors, also the empty minor, then what you get is this determinant. If f is equal to d and g is equal to d, so f and g are the same, and so you get d star d, which is actually the zeroth Laplacian, L0 Laplacian. What you get is then you count the number of trees. These are actually just, each of them is just non-zero if and only if you have a tree. And in this case, it's non-zero if and only if you have a forest. Now I mentioned this because what happens is this superdeterminant comes in for the definition of the analytic torsion. So what you do is the only thing you change from the superdeterminant is you just have a k here. So you can also start with k plus 1 if you want. So these determinants enter here in a kind of a weighted way. I call it the analytic torsion for graph. But this is an extremely important, interesting quantity because it's very subtle. So it's not a homotopy invariant, for example. You just change, this is a homotopy step here. You take a vertex where the unit sphere is contractible and you take it away. That's a homotopy reduction. You could also add something, and you add something here. That's also a homotopy step. And so under homotopy transformations, these numbers change. So it's quite an interesting thing. But there are cases where it doesn't change, and I will come to this. So there are cases where it is really an interesting topological quantity. Manifolds appear to be among them, and contractible category 1 spaces. So this is a spectral quantity. Of course, it's just defined only by the eigenvalues, and you take the non-zero eigenvalues of the Lk. So you kind of disregard the cohomology. But in some sense, this actually seems to depend on the cohomology also. It is just taken essentially word by word from the analytic torsion which you have for manifolds. But for manifolds, it's very, very complex, because what you have to do is you have first to define the determinant of a Laplacian, like a elliptic operator. You have the eigenvalues, the non-zero eigen. You take the non-zero eigenvalues of such an elliptic operator, and then you take this zeta function. But of course, that doesn't make sense even for the circle where you have the eigenvalues are k square. Right, you multiply these squares, and so what you get is a value which only makes sense in an analytic continuation form. So that's maybe why it's called analytic, because you really need analysis. You need complex analysis to make sense of this. For example, for S which are negative. So formally this is actually just a product of the non-zero eigenvalues, but of course it doesn't make sense kind of in a calculus setting. You need this theory of analytic continuation to define this, which makes it more complex and also more difficult to compute. So sometimes we can compute it, like for the circle, when we know all the eigenvalues of the Laplacian. This is something you learn in linear algebra. You have the e to the I kx are the eigenfunctions, and the k square is are the eigenvalues, and I think minus k square is the eigenvalue of the second derivative, and then you have the k square, and then you can compute that. And in this case, the analytic torsion is 1 over 2 pi. So you can compute it in cases where you know all the eigenvalues, but in general, it's difficult to compute this quantity. Even if you know the eigenvalues, you have to analytically continue it. And in this case, it was the Riemann zeta function where we know how to analytically continue. I mention this because just classically in analysis, you have very hard analysis involved here. There's elliptic regularity, for example, which is involved just to know that the eigenvalues are discrete. The spectrum is discrete, and all kind of technical things which you need. Also, Hodge theory is more technical in the continuum. Here we are in a linear algebra setting. We have matrices, we have eigenvalues, we can compute this. This is, again, this whole thing takes until here, that takes maybe 6 lines of code to write down for a general graph. So you can make experiments, and that's what I did in 2015. I write about contractibility. Contractibility is a recursive definition. Contractible means the graph is contractible if you can take a vertex away with all the connections such that the remaining thing is contractible. So this graph here is not contractible because you can take everything away except in the end what you end up is with the circle here. With a circle with a C4. This C4 is not contractible. So this is a circle, this is a sphere. And so contractible is, from a Luster-Schneermann point of view, these are category 1 graphs. And they can be covered by one contractible thing. So a D-sphere is just a D-manifold, such that if you take a point away, it becomes contractible. And a D-manifold is a graph such that every unit sphere is a D-1 sphere. So that's all recursively defined. And the 0 sphere is the -1 sphere is the empty graph, and inductively also the K1 is a one-point graph deemed to be contractible. So here are experiments which I did. So if G is homotopic to 1, then I see that the analytic torsion is always equal to the number of elements. So this is huge numbers coming here, because these determinants essentially count higher dimensional trees. So in general, this seems to be kind of, when you have contractibility, that it's really a homotopy invariant when it's contractible, but in general it's not. It's a mistake which Whitehead did. What I see also for odd dimensional spheres, it's just the number of maximal simplices times the number of vertices. So that's for even dimension. This is for odd dimension. For odd dimension, like for a circle, when you look at the circle, for example, then you get here, for example, you get a square. For this one sphere, one can just show it because you know everything, you know the eigenvalues and everything. So that would be kind of the first thing to do. Maybe prove it for 2 spheres. 2 spheres are graphs such that every unit sphere is a circular graph with 4 or more elements. I also see something interesting, or saw something interesting which I cannot prove, and I don't know whether it's related, that I looked at the pseudo-determinant of D, of the Dirac operator, a tree interpretation. Strange way, because you have to count trees with different signs. And what I see is actually that the determinant, the number of vertices times a square. That would suggest somehow that D is again a square of some. So we know L is just V squared. That will actually mean that the determinant of L is V squared times a power of 4. Show you an example. And the whole thing is just for A and D, this I can kind of for complete graphs where everything is known, you know the number of vertices, number of edges, you know the number. So this is all the binomial numbers, which is in general not a homotopy invariant. Already, if you have a circle, if you have one, if the fundamental group is not trivial, And just here is a little bit of history. So that was first done in the 30s. Reidemeister and his student Franz, and then in Switzerland George de Rham, Ray Singer in the 70s. Giger and Müller have then shown that two different notions, Reidemeister torsion and analytic torsions, are the same. And it was also used in the context of three manifolds or of knots. So Reidemeister is also appearing in knot theory. That was something done in the 60s. So it's a very interesting topic. Combinatorics actually here, or linear algebra. I just wanted to share this so that it doesn't get lost in my hard drive. In my age, you never know, what you still can do. Okay, that's it for today. I think that's also it for the year.